In 2013, CASW established a new tradition for the New Horizons in Science Briefings, the Patrusky Lecture. This annual lecture honors Ben Patrusky, who served as CASW's executive director for 25 years and as program director for New Horizons for 30 years. The Patrusky Lecture is meant to provide a big picture view of a broad scientific field and the scientific enterprise itself. This year's lecturer, planetary scientist Steve Squyres, fits that purpose perfectly. But for me, there's also a personal connection. I'm sure Steve doesn't remember this, but I met him more than 20 years ago during a AAAS meeting in Seattle when he gave a talk about Europa, a mysterious ice-covered moon of Jupiter. It was the first AAAS meeting I ever attended as a science journalist. And by the way, I looked up the title of the session on archive.org, and the subject is just as provocative today as it was back in 1997. Could Europa harbor submarine hydrothermal life? Since then, I've covered Steve's work primarily in his capacity as principal investigator for the science payload on the Mars Exploration Rovers, which bounced to the surface of the red planet back in 2004. Those rovers were designed to last 90 days, but thanks to Steve and the other members of the rover team, they kept going for years longer. This February, after 15 years of discovery, Steve and his colleagues finally bid farewell to the Opportunity rover on Mars. During a career that has spanned more than 3 decades at NASA, Cornell University, and other institutions, Steve worked on other space missions as well, including Voyager, Magellan, the Near Shoemaker mission, Cassini, Mars Express, Mars Reconnaissance Orbiter, Mars Odyssey, and the Curiosity rover. Steve led the most recent National Research Council Planetary Decadal Survey and has served as chairman of the NASA Advisory Council. He's a fellow of the American Academy of Arts and Sciences, and last month he left Cornell to move up to my neck of the woods in the Seattle area. He's just beginning a job as chief scientist at Blue Origin, the space venture founded by Amazon CEO Jeff Bezos. During today's talk, Steve will look back at the Spirit and Opportunity missions on Mars, and he'll also look ahead to the future of planetary exploration. If he doesn't mention the moon and Europa, I'm definitely going to ask him about it during the Q&A. But first, we need to go through one of the traditions associated with the Patrusky Lecture, the award of a certificate and a Patrusky prism to mark the occasion. Steve, I hope you'll accept these tokens of our esteem and perhaps display them in your new office at Blue Origin.
So let me get the legal stuff out of the way first. I am not here representing my current employer. I'm just here as Steve the Mars rover guy. And I'm going to talk today, actually not about the moon or Europa. I'm sorry. It's going to be all Mars, but when we get to the questions, let it rip. It's a very exciting time in the space exploration business. For the first time in many years, we are talking in a serious, meaningful way about sending humans once again beyond low Earth orbit and doing it this time to stay. And there's talk of humans to the moon, there's talk of humans to asteroids, there's talk of humans to Mars. What I'm going to try to do in my talk today is offer you my opinions, and they will be just that, my opinions, on the issue of sending humans to Mars. And I will base those opinions almost entirely on personal experience, most of it having to do with operating some vehicles on Mars for 15 years, and also a few other things that I've done with my time. At the end, I'll tell you what I think, and you may agree, you may disagree. So this is Mars, the object of our affections. It's a pretty tough place to do business. The annual average temperature is about 60 degrees below 0 Celsius. It goes down to minus 100 Celsius at night. If you took all the water vapor in the Martian atmosphere and you condensed it out on the planet's surface, you would make a layer of frost that is barely 1/100th of a millimeter thick. So it is today, and for most of its history has been, a cold and dry and desolate world. Now, as we think about sending humans to Mars, the first thing to recognize is that the idea of sending humans to Mars has had an enormous hold on the human consciousness for a very long time. This is from the wonderful movie The Martian. People have been talking about sending people to Mars for a very long time. It's a romantic notion. It's an appealing notion. And the literature of science fiction is full of stories of humans going to Mars to explore, humans going to Mars to stay. Now, I'm going to suggest that there's sort of three ways, these are not the only ways, but there are three useful ways of looking at how humans might go to Mars at some point in the foreseeable future. And I'm not going to try to look out millennia into the future. I'm not going to try to go multiple centuries in the future. So we'll have our horizon be, a century or two, okay? Beyond that, my crystal ball is too cloudy. One model is a research base. What you see here is Amundsen Scott Station. This is at the south pole of the Earth. Very tough place to live. Yet there's a permanent research base there, and people go there and they do meaningful scientific research. I've been in Antarctica 4 times myself. I have not been to the South Pole, but there are these research bases in multiple locations on the Antarctic continent. So that's one way that one can envision going to Mars, is setting up a research base where people go, do their work, and then come back home. Another is tourism. If you are wealthy enough to afford it, you can buy a berth on a cruise ship, and you can sail to Antarctica. And many people have done that. And you get to visit the continent, experience it, admire its beauty, and then again, you go back home. So space tourism focused on Mars is another possible model of how this might work. A third is true colonization. People go there to live. They live their entire lives. They live, they die. Generations are born. You raise babies on Mars. This is a place, one of my favorite places on Earth. This is a place called Longyearbyen. This is the capital of, if you will, of the archipelago of Svalbard. Svalbard is north of Norway. It's about 600 nautical miles from the North Pole. And there's a town. Longyearbyen, I think, is about 2,000 people. You know, there are banks, there's an elementary school, there's a swimming pool. People live there. They raise their children. And one can imagine, even a fairly robust setting, actually going there and people going to Mars to live. So those are the three possibilities that I'm going to consider. Now I'm going to spend some time telling you about Mars, and we'll come back to the end and I'll tell you which ones I think might work. So this is a picture. This was taken at Cape Canaveral, long time ago now. This was taken in 2003, shortly before we launched the Mars Exploration Rovers off to Mars. You can see this rover Spirit in the foreground, all tricked out and ready to go to Mars. If you look in the background, you can see the Opportunity rover against the far wall. I'm the good-looking guy in the white suit. These vehicles were our surrogates. We built them to have as human-like qualities as we could give them, and then we experience Mars through their sensors. The spacecraft that we built to get the rovers to Mars is like one of those Russian doll sets where there's a doll inside a doll inside a doll. You can see the rover at the far right, and what it does is it folds up in this horrifyingly intricate fashion to fit inside a lander. The lander structure you can see at the lower right, 3 colorful things on the sides of that in that illustration, we call those petals because they're like the petals of a flower. And those petals fold up around the rover, encasing it, protecting it for the long trip to Mars. And when it's all folded up, you can see sort of in the middle there, it forms a tetrahedral pyramid. Now that is then encased in turn in another shell. The front part of it, shown at the bottom there, that's the heat shield that protects the vehicle during the high-speed descent through the Martian atmosphere. And there's a cone-shaped thing on the back of that that's called the back shell. And so that's another shell that protects the vehicle. And then the kind of blue frisbee-looking deal on the top of it, that we call the cruise stage. The cruise stage provided electrical power, propulsion, the stuff you need to get you to Mars. The trip took about 7 months. This is a complicated plot, but it makes a simple point, and that is you cannot depart from Mars whenever you want. Not with the propulsion systems that we have today, nor those that we're likely to have anytime soon. You have to wait for the planets to properly align. In the case of our mission, and in the case of most future missions, the period of time between launch windows is 26 months. And if you miss that 26-month launch window, that launch window, you don't get to go again until 26 months. And in our case, we had to hit that window in the summer of 2003, or we were not going to go to Mars at all. We were spending $1 million a day. Nobody was going to keep us going for 26 months. If we didn't launch then, our rovers were not going to go to Mars. They were going to go to the Air and Space Museum. And not out on the floor with the good stuff, down in the basement with the stuff that never flew. You can't argue with Isaac Newton. When you get to Mars, you hit the top of the Martian atmosphere going Mach 27. 27 times the speed of sound. That heat shield bleeds off kinetic energy. And once the vehicle has reached a nice leisurely Mach 2, we throw out a supersonic parachute. You can see that at the upper right. We learned the hard way that supersonic parachutes are very difficult things to design and build. The lander descends on a long cord, and you can see at the lower right what the vehicle looks like as it's still screaming down towards the Martian surface at about 200 kilometers an hour. You don't drift down lazily on a parachute on Mars. The atmosphere is very, very thin. It's a really hard place to land. We had a terrible time with our parachutes. These are some pictures from the test that we did, the first test that we did of the parachute design that we thought was going to land us on Mars. We did this test at a National Guard gunnery range outside of Boise, Ohio. It's the kind of place where you can drop big, heavy things from the sky and they won't kill anybody. We dropped our test article from a Chinook helicopter at 4,000 feet. It fell, deployed the parachute, it made this perfect orange and white bowl, and then it just exploded. It ripped to ribbons. And parachute after parachute failed. What we realized was that as our understanding of the design of the vehicle that we had to land matured, our estimate of its mass grew. And by the time we did this test, the vehicle was too heavy for the parachute to function properly. We embarked on a crash program of parachute redesign. We designed 3 parachutes in parallel, praying that one of them would work. One of them did. This is a picture of a test of the parachute design that actually landed us on Mars. We had our first successful parachute test 8 months before we had to be on top of the rockets in Florida. It was terrifying. We land using airbags, as Alan mentioned. They're like the airbags in your car, but a lot more expensive. They inflate explosively around the vehicle about 10 seconds before touchdown. About a second or two before touchdown, you can see at the upper right, rocket motors fire. We cut the airbags free. They fall to the surface, and they bounce. They bounce, and they bounce, and they bounce, and they roll, and they roll, and they roll. And they can bounce and roll as much as a kilometer before the vehicle comes to rest. And at the lower right, you can see an airbag engineer at JPL being consumed by his work. We had a terrible time with the airbags as well. You can sort of tell by the picture at the lower right, they're not having a good day. This was the first test of the airbag design. And we did it at the world's largest vacuum chamber in Sandusky, Ohio, taking the bags and whacking them down on a platform that was studded with sharp, pointy rocks. And they burst. They ripped. We had to redesign those. The only way to solve that problem was to brute force it by making the bags stronger, reinforcing them, adding more layers of fabric, which made the whole system heavier, which made the parachute problem worse. We got it to work. On the left, you see a picture from one of our first successful parachute tests. On the right, the ultimate test, those are parachute, or airbag, rather, bounce marks on the surface of Mars. This is what the vehicle looked like when we put it all together. This is a big thermal vacuum chamber at JPL. We launched in the summer of 2003, 2 launches on Delta II launch vehicles, 1 in the daytime, 1 at night. And as I said, it took us 7 months to get to Mars, and we got there in January of 2004. Landing was very tense. One of the most memorable, 2 of the most memorable nights of my life. You can see me at the lower right there with hair that was a lot less gray than it is right now. But when it works, it feels really, really good. Let me tell you a little bit about some of the science that we did. I could talk for hours about the scientific accomplishments of Spirit and Opportunity. As Alan mentioned, they were each designed to last for 90 days. We got 6 useful years out of Spirit and 14 and a half useful years out of Opportunity. So the scientific return that we got from the vehicles was immensely more than I could have imagined in my wildest dreams, and I had some pretty wild dreams. You can see here the landing site for Spirit, that great big blue crater in the middle of this image, the topographic map. It's called Gusev Crater. It's 160 kilometers in diameter, 16 degrees south latitude on Mars. The reason we chose it is if you look to the south of that crater, there's a great big dry riverbed flowing into the crater. Now, there's no water in that river now. There hasn't been for billions of years, but it was carved by water. There has to have been a lake in Gusev Crater at some point in the distant past. And so we went there searching for layered sedimentary rocks laid down billions of years ago in a Martian lake. We did not find them. What we found was that the crater was full of lava. Mars faked us out. I'm still convinced that those sediments have to be down there somewhere, but they had been buried with lava. Fortunately, the rover lasted long enough that we were able to drive it well farther than its design distance to a wonderful range of hills that we named the Columbia Hills after the Columbia Space Shuttle. And we spent hundreds of Martian days climbing to the top of the highest summit in the range. We named it Husband Hill after Rick Husband, who was the commander of the Columbia when it went down. This is the view from the summit of Husband Hill, looking to the south. And most of the most important scientific discoveries from Spirit's mission actually came after we crested Husband Hill and went down the other side. I'm just going to tell you about one of my favorites. It took place right here near a place that we call Home Plate. About 800 sols, that's a Martian day, about 800 Martian days into Spirit's mission, the right front wheel failed. So it would no longer turn. And in order to drive the vehicle, we then had to drive it backwards, dragging the dead wheel through the soil. And a rover that used to do 100 meters in a day, a good day was now 5 meters. But there was a silver lining, and that was that that dead wheel dug this marvelous hundreds of meter long trench through the Martian soil. Pure serendipity. We never would have done that on purpose. But wonderful things would pop up in the floor of the trench. We were driving one time through a little valley, and at the end of the drive, the soil in the trench popped up as white as bright snow. This caught our attention. We went over and looked at it with our spectrometers. It was not snow at all, nothing of the sort. This stuff was more than 90% pure silica, SiO2. It's not quartz, it's not crystalline, this is not beach sand. This was opal. Hydrated amorphous silica. This was opal like the gemstone. This is the stuff that you find in hot spring environments on Earth. This was telling us of a hydrothermal system that once existed at this location on Mars. So this was compelling evidence that in this little valley that had these silica deposits, long ago there had once been a habitable environment. Of course, we named the place Silica Valley. Many more discoveries from Spirit, which I don't have time to tell you about. Let me go to Opportunity. This shows Opportunity's landing site We chose the landing site for opportunity not because of the topography. No hole in the ground, no dry riverbed. We chose it because of its composition. The image at the upper right is from an infrared spectrometer in orbit, and it shows the occurrence in the upper right there, the red, yellow, and green, of a mineral called hematite. Hematite's an iron oxide. It is a mineral that's present in rust, and it usually forms as a result of the action of liquid water. So this was like a chemical beacon, visible from space, saying, hey, water may have been here, come land here. Now at the lower left, you can see an image of the topography, wonderfully smooth, wonderfully flat, safe for landing, safe for driving. It's a terrific site from a safety perspective. The thing that made me nervous about this landing site was I was concerned that it was so smooth and flat that nowhere would we find the topography necessary to expose bedrock to our instruments. I need not have worried. These are some of my favorite images from the entire mission. As our vehicle was descending towards the surface, it had on its underside a camera mounted that was looking down. And it had just enough time to snap off 3 pictures on the way down. You can see those 3 pictures at the upper left. If you look at the far right of that image, there's a crater. And just to the left of it, you see a little black dot. The black dot's the shadow of the parachute. Okay, and then the picture at the bottom just shows the same view illustrated obliquely. Now the red curve is the reconstructed trajectory that our vehicle went through as it went through the landing process. So we're coming in from the left, we're coming screaming in from space, 200 kilometers an hour. We get close to the surface, we fire the rocket motors, drop the airbags to the surface, and they begin to bounce. The wind that day was blowing from the south. So the trajectory bends to the left, bounce, 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 and then reading the green perfectly, it curves gently to the left and goes right into a little 20-meter diameter impact crater. Tiger Woods, on the best day he ever had, could not have pulled this off. Now, it was just pure dumb luck. We opened our eyes, and there was a magnificent outcrop of layered bedrock right in front of the rover. And over a period of about 60 Martian days, just staying initially in this tiny little crater, we made a series of extraordinary discoveries. I'll just tell you one of my favorites. When we first drove off the land and we looked down at the soil, looked at it with our microscope, we saw that it was littered with an uncountable number of little round things. They were 4, 5, 6 millimeters in diameter, and they were absolutely everywhere. And initially, we had no clue what we were dealing with. We drove over to the outcrop. What we discovered is that the little round things are embedded in the outcrop like blueberries in a muffin. The muffin is soft, the blueberries are hard, the muffin would erode away, and the blueberries would fall out. And they're absolutely everywhere. This is a picture taken with our microscopic imager, a couple centimeters across, and you can see the little hard blueberry embedded in the layered muffin rock. After studying these extensively, what we came to realize was the blueberries, which are made of hematite. That's where the hematite signature comes from, is those blueberries. The blueberries are what geologists call concretions. Concretions form typically in sedimentary rocks on Earth that are saturated with liquid water. There is some mineral, like hematite, that is dissolved in the water. It is supersaturated. It wants to precipitate out. It finds a nucleation point. It starts to precipitate. And then you create a concentration gradient, so stuff diffuses down that gradient, and it adds layer upon layer upon layer, building a little hard spherical nodule in the rock like the way an oyster builds a pearl. So this was compelling evidence at this place that liquid water had again once been present. So many scientific discoveries by opportunity that I would love to tell you about. Don't really have the time to do that in this format. I'll do one more for you. Late in Opportunity's mission, we drove to a very large crater, 22, 23 kilometers in diameter, that we named Endeavour. And as we pulled onto the rim of Endeavour crater, we saw this. Multiple places on the ground. It looked like somebody had taken a can of white paint and a paintbrush and had painted white stripes on the ground, nice straight white lines. We went and looked at them, and what we found was these were veins of some kind of mineral. And we measured its composition. What we found was this was essentially pure gypsum, calcium sulfate. Calcium sulfate salt gets precipitated from liquid water. So this is a place where there were fractures in the rock, and at one point, billions of years ago in the past, liquid water flowed through those fractures, precipitated out these gypsum veins. So again, compelling evidence of the action of liquid water at the surface of Mars. Now, there were many wonderful scientific discoveries, but I don't want to give you the impression that we had an easy time of it. We had a very hard time of it. Mars is a tough place to do business, and I'm going to try to give you a little bit of a sense of that. It's a hard place to drive around. In order to get to Endeavour Crater, Opportunity had to do a 20-plus kilometer drive. And that involved, at one point during the mission, driving through a little dune field. Now, initially, as we left our very smooth landing site and worked our way into this dune field, we were doing great. We would go over one dune and over another and over another. We were basically trying to set records for how far we could drive in a day. I think our all-time record was like 204 meters in one Martian day. We were using a mobility technique that I will describe generously as bombing along at top speed with our eyes closed. And it bit us. As we got farther south, these little dunes got bigger and bigger. And one terrible day, we hit one, and I still don't completely understand this, but we hit one that was just a little bit different from all the others. And the wheels broke through a crust, and we did 50 meters worth of wheel turns, thinking that we were driving happily across the plains, and in fact, we were just digging ourselves deeper and deeper and deeper into the soil. We came in the next morning, and all 6 wheels were buried over the hubcaps. This was a bad day. Now, the first rule in a situation like this is don't do anything stupid that's going to make the problem worse. Okay, the sun is shining. We got plenty of power. The rover's obviously not going anywhere. We got time to work this out. Now, when we built the rovers, we actually built 4 of them. 2 of them, Spirit and Opportunity, went to Mars, but there were 2 more back on Earth that would use to simulate predicaments that we got ourselves into and then try to work our way out of them. This is one of those 2 rovers. This was just very recently shipped to the Air and Space Museum, where it's going to go on display soon. In order to simulate this particular predicament, we needed a very large quantity of fake Martian soil. If you're ever called upon to create fake Martian soil, here's the recipe I recommend that you use. It's equal parts play sand, the stuff in kids' sandboxes, clay, and diatomaceous earth, the stuff that's used in swimming pool filters. Once we worked out this recipe, a bunch of engineers in pickup trucks fanned out across the LA basin and brought up literally tons of these 3 ingredients. People were getting algae in their swimming pools all summer long because of us. We brought it back to JPL, mixed it up, drove the rover into it, and then we spent 2.5 weeks rehearsing, trying to figure out the optimal way of extracting a robot from a sand dune on another planet. There are a lot of things you can do. You can run the wheels at different velocities. You can rock the vehicle. Okay, you can steer the wheels back and forth to try to open up the holes that they're in a little bit. We tried all of those, many others, and after 2.5 weeks, we found the optimal technique. The optimal technique was to put it in reverse and gun it. There's no place you go to look this stuff up, okay? Anyway, here we are, gunning it on Mars. Time-lapse image here. We were in bad shape. That's the left rear wheel. We had to do 192 meters worth of wheel turns to get the rover to move 1 meter. But one wonderful Saturday morning, after 6 weeks stuck in a feature we later came to call Purgatory Dune, the vehicle popped out, and we treated those dunes with much greater respect from that point forward. Dust. I guarantee you that when the first astronauts come back from Mars and people say, what was it like? One of the first things they will say will be, I hated the dust. This stuff is everywhere. Now, I told you at the beginning I liked the movie The Martian, and I did, but that storm at the beginning with the gravel flying around, no. Mars does not do that. When you think about dust on Mars, don't think about gravel, don't think about sand, think about cigarette smoke. Micron-sized particles, cigarette smoke. So I love that movie. I thought the storm at the beginning, they could have found a better way to strand Matt Damon on Mars. Okay, other than that, good movie. But that dust gets everywhere. And even though the Martian atmosphere is so thin, it is capable of suspending dust. And then that dust settles out and it coats everything. This is a rover selfie. This is a picture that Spirit took, I guess, about 250 days into the mission. Now, when the rover was brand new, straight off the showroom floor, clean solar arrays, full sunlight on the arrays, those solar arrays would put out about 900 watt-hours of power per Martian day. Enough energy at 900 watt-hours to run a 100-watt light bulb for 9 hours. As the dust accumulated, that energy output went down, 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 and down. And at the time this picture was taken, it had dropped from 900 watt-hours down to about 250. And death is somewhere around 150. So Spirit was close to the end. And then one wonderful day, this happened. Lucky gust of wind, overnight, hit the vehicle, and the power overnight went back up to 850 watt-hours. Pure dumb luck. It was as if this had happened. What actually happened may have been more like this. These are dust devils, little Martian mini tornadoes. You can almost see Dorothy and Toto flying through the scene here. But we may have been hit by one of those that kind of vacuumed the dust off of the solar arrays. But that dust is a serious problem. The dust accumulates and then is sometimes removed in a pretty repeatable way over the course of the year. This is something that we call dust factor. It shows you how much dust there is on the arrays. With a dust factor of 1, that's a perfectly clean array. A dust factor of 0 means that no sunlight gets through at all. And this is dust factor as a function of time. And what you have at the bottom is the Martian year, winter, spring, summer, fall. And you can see it is fairly repeatable from year to year. So there are some periods in which dust accumulates and other periods in which dust gets taken away. But it is constantly in motion and is a constant issue on the planet. Then, Mars, from time to time, experiences global dust storms. These global dust storms, when they occur during the southern hemisphere summer. That's when the maximum heating of the surface by the sun takes place. That's when you get the maximum energy input into the atmosphere, stirs up the winds, and gets the dust going. And in a matter of just weeks, you can go from a really nice view of the planet as seen from space to everything essentially completely obscured. It doesn't happen every year. We experienced, over the course of 15 Earth years on the surface of Mars, we experienced 2 global dust storms. The second one, just last year, was the one that put an end to the mission. That was the one that killed Opportunity. There was another one, not too long after we landed, and that caused us a lot of trouble. This is 1,200 Martian days into, let's see, that must be Opportunity. Yeah, that's Opportunity's mission. You can see how things looked. There's a parameter called tau, which it's a measure of the atmospheric opacity. Higher it is, the more opaque the atmosphere. You can see it at left, normal conditions. At right, getting into the depths of a pretty bad dust storm. Now, if you were on the Martian surface, standing there in your pressure suit, and there was a wind howling, blowing dust around, in that big stiff suit, you wouldn't even feel it. You're not going to tip over in the wind. Nothing like that happens on Mars because the dynamic pressure of that very thin atmosphere, even at high velocities, 100-mile-an-hour wind, exerts very little dynamic pressure on any surface. So again, Matt Damon wouldn't have gotten blown over in the wind. But the dust gets everywhere. Again, it's semi-repeatable from year to year. This is that atmospheric opacity measure. Low is a clear atmosphere, high is an opaque atmosphere, and you can see this is multiple Mars years, pretty repeatable from year to year, especially in the first half of the year. And then the second half on this plot, when it's just getting into southern summer, you see that some years there are these big spikes, and those are the dust storms. The first dust storm nearly killed both rovers. The second one did kill Opportunity. This is just a plot. The main thing to look at is the blue curve, and this is the solar array energy in watt hours. We started off the storm at about 700, and then day by day it dropped and dropped and dropped and dropped, and it dropped down below 200. So this was nearly a very, very bad experience for the rovers. They survived this one. Temperatures. Mars is brutally cold. There are two bad things about the thermal environment on Mars. One is that it gets incredibly cold at night. This is the temperature of our solar array. So this is a surface on the rover that gets illuminated directly by the sun. So this is warmer than the atmospheric temperature in the daytime because you got direct sunlight on it. Okay, you see in the daytime, surface temperatures can get as high as 0, maybe 10, 20 degrees C. But look at the nighttime temperatures, minus 100. And this is near the equator. It is a brutally cold place. The other thing to note is the enormous differential between daytime and nighttime, more than 100 degrees C. So everything you build that gets exposed to the surface environment expands, contracts, expands, contracts, expands, contracts every 24 hours and 39 minutes, the length of a Martian day. So it's a very tough thermal environment, but it is incredibly cold at night. And the mean temperature, the average temperature, the temperature that things will equilibrate to, if you build a piece of hardware, a habitat, anything like that, the temperature it will equilibrate to without heat to keep it warm is minus 60 C. Minus 60. There are seasons on Mars. The seasons are similar to those of Earth. They result from the obliquity, the tilt of Mars' spin axis being almost the same as on Earth. And we always thought, even if the dust accumulating on the solar arrays didn't kill us, we were always convinced that the first winter on Mars would kill us. And the reason for that is that we were in the southern hemisphere, and in the winter, the sun goes very low in the northern sky. And so with that sun low in the northern sky, we had no capability of tilting our solar rays towards the sun. We couldn't articulate them. And so you did the math, and it said the rover's not going to survive, even with reasonably clean solar arrays. So we always knew the first winter would be fatal. We weren't thinking hard enough. We designed these for landing sites that were very smooth and flat. And so all of our calculations, we assumed that the rover was on flat ground. But what happened was we were able to cover so much ground that by the time winter came, we could be on hillsides. We could be in the mountains. And I showed you earlier that picture of our route up Husband Hill, and if you looked at it carefully, you will notice that we didn't just go blasting straight up the West Ridge. We could have. Would have killed us, but we could have done it. Instead, we drove around onto the south face. around onto the south face. And what that did is in the wintertime, it tilted the rover pointing the solar rays towards the sun. The whole rover tilted. And so what we would do when we were driving is we would make maps, and this is one of them here from the mission. We would make these maps that showed the angle of sunward tilt of the terrain. And we called these lily pad maps. And the places that have good sunward tilt are the ones shown in red. And what we would do was we would drive from one red spot to another, like a frog hopping from lily pad to lily pad on the surface of a pond. And at each of those spots, the solar rays were tilted towards the sun, the power was good, and we were able to survive. And we survived multiple winters on Mars just using this straightforward trick. Mars time. The Martian day, as I said, is not 24 hours long. It's 24 hours and 39 minutes long. You might think that being able to sleep in an extra 39 minutes a day is a good thing. It is not. Not if you live on Earth. For the first 4 months of the mission, all of us who were entrusted with the care and feeding of the vehicles lived on Martian time. They're solar-powered vehicles. They didn't care if it was daytime or nighttime in Pasadena. They only cared if it was daytime or nighttime in their landing site. And what that meant was that our schedules had to be, our days were 24 hours and 39 minutes long. So if our daily operations meeting started at noon today, the next day it's going to be at 12:39, and the next day it's going to be at 1:18, and it works around the clock, and 2.5 weeks later you're getting up in the middle of the night. Thank God for grad students. And we had to live on that schedule. Moreover, we had 2 rovers on the surface on opposite sides of the planet. So I had to split my team in half, some working on Spirit, some working on Opportunity. So I got everybody living on Mars time, but in 2 very different Martian time zones. And if you were working on one rover and you want to switch to the other, you would get Martian jet lag. So it was a very difficult experience for us in some respects. Now, the interesting thing, though, was for most of the team, for most of the science team was living in Pasadena, away from their homes, away from their families. We had found apartment complexes where we could get, housekeeping service on Mars time. We had food service on Mars time. We had blackout curtains on the windows. And what we found was that people who were able to live on that schedule could pretty much cut the cord with Earth entirely. And if you cut the cord with Earth entirely and switch over entirely to Mars, it's easy. 24:39 is close enough to 24 hours. It's fine, and you do actually get to sleep in an extra 39 minutes each day. Now, in my case, I had to be at a lot of press briefings. And the press briefings were 8 a.m. Pacific time every morning. Earth time. We couldn't have Mars time press briefings. I wish I'd been able to put all you guys through it. But yeah, there were days when I would work a full, 10-hour shift at work, go home, go to bed, set the alarm to wake up in 3.5 hours, come in, do a press briefing, and go back home to bed. If you can cut the cord with Earth, though, Mars time is pretty straightforward for the people on Mars. For the people back on Earth who are interacting with them and keeping their schedule, it's going to be tough. All right, slight diversion. I want to talk about one-way light time and the separation between Earth and Mars and what that means for people living on the surface. I had the very interesting experience some years ago, and how long has it been now? 7 or 8 years, of being a crew member on a project that NASA calls NEEMO, N-E-E-M-O, NASA Extreme Environment Mission Operations. It's conducted by NASA at a habitat in about 60 feet of water off the south coast of Florida near Key Largo. And it's used primarily for training astronauts. This is one of my favorite pictures from my second NEEMO mission. That's me there going like this on the extreme right. It's a funny picture This NEMO is very complex technically, a lot of stuff going on, submarines, a lot of divers in the water, very dependent on what the conditions are like. Most of the time, things aren't going just right. We had this one beautiful day, perfect day, when everything was working. The submarines were in the water, they were working, good communications, good visibility, no current, it was just perfect. And so the project manager said, okay, I want you guys to pose for the picture that I'm going to use on the first slide of every NEMO presentation I ever give. We said, what do you want us to do? He said, I don't know, just look badass. So this is us trying to look badass, and that's for real. We got photobombed by a barracuda. That was not photoshopped in. What were we doing? My missions, I was on 2 of them, our objective was to figure out how to do field geology on an asteroid. Now, most of the asteroids that can serve as useful resources in space, most of the Earth-approaching asteroids are tiny things. You don't realize that most of them are very small. This is the asteroid Itokawa. It was the one that was visited and a sample was returned by the Japanese Hayabusa mission. There it is. There's the International Space Station for scale. This is so small that it is a zero-gravity object for all intents and purposes. Its surface close up looks like that. You can see a little red 1-meter scale bar down in the lower right corner. So imagine having to do a spacewalk, an EVA, where you were working on the surface of an asteroid like that in zero gravity. Now, we have lots of experience with EVAs on a planetary surface, the moon, that has 1/6 gravity. We know how to do that. We have lots of experience on doing EVAs on the International Space Station, but asteroids don't have handrails. And so our job was to figure out how to do what this sort of fanciful illustration of somebody exploring one of these asteroids looks like, and this poor astronaut is going to take out a rock hammer, is going to whack that rock, and he's going to learn Newton's laws really quickly. Now, for many years, the way that NASA has simulated long-duration spacewalks, long-duration EVAs in microgravity, has been using this marvelous facility called the Neutral Buoyancy Laboratory at Johnson Space Center. It's one of the world's largest swimming pools, 40 feet deep. Right now, it's got the entire International Space Station mocked up in it. This is a crew that's rehearsing how to do some servicing on the Hubble Space Telescope. So this, you can use the neutral buoyancy afforded to you by being in the water to simulate microgravity. And where we did it was at this Aquarius habitat that NASA makes use of off the coast of Florida. I was very fortunate to be on 2 NEMO crews. My first NEMO mission, NEMO 15, you can see the crew at the top. We had a tough mission. The conditions were not very good for most of the mission, and then 5 days in, what was supposed to be a 2-week mission, we had a hurricane, Hurricane Rena, bearing down on us, and topside they made the decision to evacuate us from the habitat. So we had to do an emergency evacuation from the habitat. They pulled us out, and we didn't get most of our job done. So I was very fortunate. This NEMO is used mostly for astronaut training because it's very space-like. But I was like the one kid who got held back in 5th grade and had to repeat it. Okay, that was me. And I got to repeat NEMO and do NEMO 16, where we had great conditions and a very successful mission. As I said, what we were trying to do was simulate. For the most part, we were focused on simulating operations at an asteroid and trying to figure out how to do that. And the technique, this is me on the seafloor doing an asteroid surface EVA. And the technique that we found worked best was this, that you have a small spacecraft. The spacecraft has the ability to position astronauts near the surface of an asteroid. Your feet are clipped into a platform. Your hands are free. Platforms like this have been used on International Space Station and the shuttle for many years. It's a great way to get the job done. So that was the primary finding. Now, the other thing that we did on these missions was, especially NEMO 16, we conducted the entire NEMO 16 mission with a couple of brief exceptions, at a 50-second delay between Earth and our habitat. So when we communicated with the people topside with mission control, there's a 50-second one-way delay. And that number was chosen because it's typical for an asteroid mission. This was the first simulated mission ever done by NASA that put in a time delay. And what we found was that it rather dramatically changed the communication situation. Then, for part of NEMO 16, we did it with a 5-minute delay to simulate Mars. Now this picture, this is from NEMO 15. NEMO 15, we were using real-time communications. We spent almost every day on NEMO doing simulated EVAs. I spent most of my time either outdoors or supporting people who were working outdoors. But there was one day in which we focused on simulated emergency scenarios. They didn't tell us what they were going to hit us with. They just said, be ready. So on NEMO 15, one of them was we simulated a fire in the habitat. The other one was a medical emergency. And the medical emergency was somebody goes outdoors, they get a serious jellyfish sting, have an allergic reaction to it, and it's kind of a life or death situation. Now we were very fortunate on that mission that, let's see, second from the left in the top row, one of our crew members was David St. Jacques. He's a Canadian astronaut. David's a medical doctor. So we aced it. He knew exactly what to do. We just blew through it, didn't even have to talk to topside. They had one of the habitat technicians, there were two of them down there too, played the victim. David saved his life and it was all good. Then came NEMO 16. NEMO 16, we ran the exact same scenario, but we did it with a 5-minute Mars-like delay. 5 minutes one way, 5 minutes the other. On NEMO 16, we did not have any medical doctors on the crew. There was an ESA flight surgeon who was topside, and he was there to help us. Now, I kind of had fun on this one because we were doing the same scenario we'd done on 16. So I knew the story. I knew exactly what you were supposed to do. I remembered it well, so they said, okay, Steve, you get to be the victim. So I came staggering in with my arm, and I collapsed on the floor, and they're trying to figure out what to do. And we got this great medical kit, and we got communications with a 5-minute delay to a talented flight surgeon. I died. I died in the scenario. Now, there were two interesting things about that. One was that the crew had forgotten to put the little sign up in front of the webcam saying this is only an exercise. So that led to some unintended consequences. But on top of that, what I took away from it was that when people go to Mars for real, the entire paradigm of mission control, the entire paradigm that has existed for decades, okay, since Alan Shepard, of how we interact with people in space is going to have to fundamentally change. When you're at Mars, in any kind of dynamic situation, you're on your own. That one-way light time to Mars can be as long as 20 minutes. A lot can happen in 40 minutes in an emergency situation. It fundamentally changes the equation. Let's see. Mars isn't all bad. There's some fun stuff. Check this out. This is one of my favorite things that we did early in the mission. That's the moon Phobos, one of the Martian moons passing in front of the sun. This is the first solar eclipse ever witnessed from the surface of Mars. There was no science in this observation at all. We just did it because we could. And that's a Martian sunset. On Mars, there's this very, very fine-grained, smoke-sized dust in the atmosphere. The dust is red, and so the atmosphere is pink in the daytime. But at sunset, when it's forward scattered through the fine-grained dust, think of what happens when you're in a dark, smoky bar room and it's backlit and it gets the smoke, cigarette smoke looks blue. Okay, turns blue at sunset. So pink in the daytime, blue at sunset, it's the opposite of Earth. Opportunity Went on for 14 years, traversed, it was a vehicle that was designed to last 90 days, went for 14 and a half years, designed to drive for 1 kilometer, it drove for 45. That's the traverse that we followed. We finally ended up in a beautiful little valley that we called Marathon Valley. That was where the vehicle died. Here's the picture from Opportunity's final resting place before the dust storm hit us. Here's the dust storm. This is not a real image of the dust storm. This is simulated. The opacity of the atmosphere got so high. But this is what actually happened at our site. And you can see by the time it got to its worst, you couldn't see the sun at all. The final picture from the Opportunity rover. I spent 16 years trying to get these things to the launch pad. And then 15 years, once we got them into space operating them, this is the last image we ever got. It was a poignant moment. And you can see partway through came the end. It's got a lot of media attention. This is one of my favorites. This is from The Onion. The Millennium Falcon came to see us, you know. All right. So let me get back to my point at the beginning to wrap this up. 3 different models for how we might send humans to this terrible place. And it is a terrible place. Okay, I spent 14 years lovingly trying to keep alive machines that I lovingly helped build with my own hands and experience the Martian environment in all of its moods, all of its seasons, all of its storms. I've been there to the extent that anyone can be there. So, human research base, absolutely, as soon as possible. Mars is a compelling place to do scientific research. It is a place where the best research is ultimately going to be done by humans. I'm a robot guy, and we cannot get humans to the Martian surface, build a base there, and have them doing research soon enough for me. I pray that I live long enough to see it. I'm eating healthy foods, I'm getting lots of exercise. But as a model for how we'll do scientific research, you know, if you send people there like an Apollo crew, they spend a short while and they come back, they're not going to have time to do the stuff that you want to do. You want to have a research base and then go, and they can spend significant periods of time there and really get meaningful scientific research done. So research bases on Mars, absolutely. The sooner the better. What about tourism? It's another scenario in which you go, you spend some time there, and then you come back. You have to be very wealthy. You have to be pretty wealthy just to go to Antarctica. You have to be incredibly wealthy, like Dennis Tito on the left here, if you want to be a tourist in space today. But while I wouldn't say that anyone has shown yet that there is a robust business model, it requires there being significant infrastructure present in space. There are enough people who are thinking hard. Here's an example from Space. There's got to be somebody from Space.com here. Anyway, this is an example of an article, company that's designing a space hotel. This is in low Earth orbit, of course. Very easy to get to compared to Mars. But there's enough interest, there's enough, maybe enough demand, I'm not sure about that, that if you ask, are we going to someday send tourists to Mars, get the research base there first, just like in Antarctica, but eventually the tourists might show up, spend a little time, and then they can go back home. So I'll give that one a check mark too. All right, let me get on to colonization. I showed you Longyearbyen in Svalbard. Okay, I showed you this picture at the beginning. This picture is beautiful, shows Svalbard, but it's kind of misleading. In the summertime, Longyearbyen looks like that. This place is 600 nautical miles from the North Pole, but it looks like that. Why? The Gulf Stream. It is embedded in the flow of the Gulf Stream, and so there's this steady stream of warm water. It dramatically affects the climate, and even though this place is really close to the North Pole, I've been there in the summertime 4 or 5 times. It's quite lovely. Okay? A better analogy is Antarctica. Now, Antarctica is international territory. If you wanted to take your family there, if you wanted to build a home, if you wanted to go homesteading, set up shop, build a community, build a town, nobody's going to stop you. You could do it. You can breathe the air. You can drink the water. There are fish to eat. There are penguins to play with. And yet nobody does it. Why? Because Antarctica is a terrible place. You're laughing, but it's a terrible place. It really is. And Mars is so much worse. Mars is so much worse. And colonization means you go there and have babies. You go there and you have babies. I'm partly in State College, Pennsylvania today because my 6-month-old granddaughter lives here. I wouldn't want her on Mars. And this idea of colonizing Mars has this enormous romantic appeal to it. But having experienced the reality of Mars for 15 years, having had other experiences that give me a sense of what it's like to be in space, I truly believe that when humans are really confronted, real people are confronted with the reality of trying to live their lives in an environment that harsh, that my take on this one is no. I don't think so. I really believe that if we're going to send humans into space to live, that if we're going to colonize space, we have to do it in a place that's nicer than Mars is, because Mars is nasty. Whenever I give talks about the Mars Exploration Rover Project, I always end them with this slide. Wrote a book about the project called Roving Mars. And in an appendix of that book, I made an attempt to list the names of everybody who had worked on the project up to the time that I wrote it. There are more than 4,000 names on the list. I'm just one of the team. This is a bunch of us. This is down at the Cape. You can see in the background, that's the Opportunity spacecraft mounted on the 3rd stage of the launch vehicle. This is the night that we went out to the launch pad. For every one of us who was part of that mission for so many years, it was, in the literal sense of the phrase, the adventure of a lifetime. And I thank you very much for inviting me here to tell you about it.
Thanks, Steve. Okay. So the bad news is that we're at the break time. The good news is that I think we can take a couple of questions here.
Go ahead.
So are there nicer places you'd like to colonize? What are they?
And we say settle, we don't say colonize.
Well, so there are other places that one could go in space that you could imagine. Asteroids are places where there could be valuable resources. Of my scenarios for Mars, I stuck to Mars. Of my scenarios for Mars, I did not include exploitation of resources. That's another scenario. Mining colonies. Those tend to be pretty rugged places to live, and they tend to be in nasty places even on Earth. I could well imagine that if there are resources on asteroids that are of sufficient value, that you would have people working there for extended periods of time, things like an offshore oil platform or some of the early mining colonies, that sort of thing. I mention those for asteroids because those are good places to get space resources. Mars is one of those places where A, there's not a lot of resource except for water, which is valuable, but B, it's a pretty deep gravity well and you got to haul it back out again. So if you ever use resources on Mars, you're probably you ever exploit resources on Mars, you'll probably exploit them there. So asteroids are a possibility. I'm particularly intrigued when it comes to mining resources by the lunar polar regions. where there are rich deposits of ice that can be used to break it down into hydrogen and oxygen and be propellants. And then, of course, there's been talk for many years about Gerard O'Neill and his ideas for building artificial space stations where people could live and work. So those are possibilities. It might be that true settlement, it might be that it'll never happen, that it's just not the right place for our species. Our species evolved in the terrestrial environment. It's pretty well tuned for us. So while I'm a big believer in trying to get industry out into space and trying to explore space and trying to settle space to the greatest extent possible, I'm also a big advocate for trying to keep this place that we have that's so wonderful, keep it still livable. Okay. Yeah.
Can you talk about the three possibilities, three scenarios for sending humans to Mars? What about 3A? Is a possibility of terraforming Mars and getting it ready?
Terraforming. Okay, I said I was only going to look a few centuries into the future. Terraforming presupposes that you have both the technology and the wisdom to tailor the climate of an entire planet to your liking. Now, one thing that we're learning on Earth right now is that the climate systems are incredibly complex things. And to me, I see no evidence that anybody knows what the technology is to terraform Mars. I don't see evidence that we have the wisdom to change a planet's climate to our liking. If we do at some point in the future, I would like to terraform Earth. So, I said I'm not going to try to gaze thousands of years into the future, and I'm not going to do that because I don't think I can look that far into the future. But I really believe that terraforming is, for now, in the realm of very deep science fiction and is going to be for a very long time to come. I don't think it's the answer. Yeah.
So there used to be these discussions where many scientists would say, we don't want to spend all that money on humans. We can do so much greater exploring using robots. You're clearly an expert on this topic. When you get humans there to do research, what's the first couple of things that a human researcher would be able to do that you just think is too far away?
Drill, baby, drill. Drill, baby, drill. That's it. Okay? Liquid water is not stable in the current Martian surface environment. And we get these intriguing hints occasionally that there might be little leaks of salty water somewhere. But if you want to find real habitable environments on Mars today, you got to go down. Okay, the average surface temperature, as I said, is minus 60 degrees Celsius. But just like Earth, Mars is going to have a thermal gradient with depth. It gets warmer and warmer and warmer. And sooner or later, and some people think it's hundreds of meters and some people think it's a few kilometers, but sooner or later you are going to get to temperatures where liquid water is stable. You can go to depths of 1, 2, 3, 4 kilometers in the Earth's crust, and there are living organisms there that are drawing from their metabolic energy, not on sunlight, obviously, but from the Earth's own internal geothermal heat. So if you want to find a place where there's a true habitable niche on Mars today, it is probably hundreds of meters to kilometers down. Drilling is hard. Okay, I was involved in the Mars Exploration Rover Project where we were able to drill this far. I've been involved in the Mars Curiosity Project where we drilled this far. Okay? If you want to drill hundreds of meters, it takes enormous amounts of power. It takes hundreds of meters of pipe. It's hard to do. You'll never do that without humans. So that would be my first one, is go for life down.
Steve, Mars Insight is supposed to be drilling this far down.
And they've had a tough time.
They're having trouble with it. Is there anything you want to say about the current troubles?
Yeah, drilling on Mars is hard. Proves my point, yeah.
So I'm actually glad that question came right before because, drilling is a huge change to what the surface of Mars actually looks like. Can you talk a little bit about the future of planetary protection?
Oh boy, yeah. Yeah, the future of planetary protection. Okay, planetary protection goes both ways, right? You worry about forward contamination, you worry about back contamination. Oh boy. We're on the record here, aren't we? Okay. Bat contamination is an issue that has to be treated seriously. I'm personally skeptical that there are organisms living on Mars that would pose a threat to humans. If they are living on Mars, they evolved very differently from life on Earth. Pathogens and their victims tend to co-evolve, right? My opinion, my guess, I'll call it a guess, is that there's nothing deadly on Mars, but guesses can be deadly, okay? I could be very wrong. So I think bat contamination we have to take very seriously. Of course, if we send humans into a Martian environment, they will be people who realize that, understand the risk that they're taking. The issue of forward contamination is a pretty serious one. Humans are dirty, dirty, dirty things. If you notice that picture I showed you right at the start, where we're wearing our clean suits in the clean room, we tried very hard to keep those rovers as free of biological contamination as we possibly could. Humans, you can't do that. And as soon as the first humans step foot on Mars, you have irreversibly contaminated the planet. And so that needs to be thought about. It needs to be thought about hard, because if you're going there to try to find life, and you're going there with life, you run the risk of putting something there and then discovering the thing that you brought. I think there are ways of dealing with this. One point is that if you find something that is human, that is terrestrial in origin, by sequencing it and looking at what you found and saying, that's a perfect match to something that we know is a robust organism that lives on Earth, you kind of got to think, okay, this is probably a false positive. The other thing is that any biologist will tell you that there is such a thing as sterile technique that you can use to sample an environment and not contaminate your sample. So I think forward contamination of Mars is a very serious issue from a scientific perspective, one thing we have to treat very seriously, but I think there are ways of doing it that will not compromise the science that we're trying to do. A good example is these drill holes that go down kilometers and try to see if there are organisms down there. And of course, you're going down there with a dirty drill bit that's been handled by people at the surface. And techniques have been developed for dealing with that and telling the deep guys from the shallow guys.
Thank you. Thanks,
Okay.
Steve.